In recent years, large language models, or LLMs, have made remarkable strides in handling long sequences of text, allowing them to understand and generate responses based on extensive contexts. However, this capability comes at a cost, especially in real-world applications where resources are limited. For instance, processing these long contexts can lead to significantly longer inference times and higher demands on memory and processing power, which is particularly problematic on devices like smartphones or edge computing systems. To tackle these issues, researchers from Oppo have developed a new method called MOOSComp. This is a lightweight approach for compressing long context inputs in LLMs, making them more efficient without sacrificing too much accuracy. The core idea is to use a token classification-based system that decides which parts of the input text to keep and which to discard, based on a BERT-based encoder. BERT, as you might know, is a popular model for understanding language at the token level. Let's break this down into the two main phases, training and compression. In the training phase, MOOSComp builds on an existing BERT-based compressor but adds some clever modifications to improve its performance. One key problem they identified is something called oversmoothing. This happens when the representations of different tokens in the input become too similar to each other during processing. As a result, the model struggles to distinguish between important and unimportant tokens, leading to poorer classification accuracy. To fix this, the researchers introduce an additional loss term called the inter-class cosine similarity loss. Cosine similarity measures how alike two vectors are in a high-dimensional space. In this case, it's used to ensure that tokens from different classes, say, tokens that should be preserved versus those that should be discarded, don't end up with representations that are too close to each other. By penalizing excessive similarity between these classes, the model learns to create more distinct and meaningful token embeddings. This is combined with the standard cross-entropy loss, which is used for binary classification, essentially, labeling each token as either preserve or discard, based on ground truth labels from a dataset. Moving to the compression phase, once the model is trained, it takes an original prompt and processes it through the BERT encoder to get token representations. Then, a classifier outputs scores indicating whether each token should be kept or removed. But here's where MOOSComp innovates further. It incorporates outlier scores. Outlier scores are designed to protect rare but critical tokens that might otherwise get discarded in a task-agnostic setup. These are tokens that don't appear frequently in the training data but could be vital for specific tasks, like unusual words or key entities in a conversation. The outlier score for each token is calculated based on how unusual or infrequent it is in the overall dataset. This could involve metrics like inverse document frequency or other rarity measures. These scores are then integrated with the classifier's output, effectively weighting the decision to preserve tokens that might be outliers. For example, if a token has a high outlier score, it gets a boost in the final decision, making it more likely to be kept even if the classifier is unsure. This makes the compressor more robust and adaptable across different tasks, without needing task-specific fine-tuning. Overall, MOOSComp is categorized as a hard prompt method, meaning it directly filters the input text rather than transforming it into soft vectors. This contrasts with other approaches like soft prompt methods, which require joint fine-tuning with the target model and can be more complex. Hard prompt methods, especially task-agnostic ones like this, are more efficient because they don't rely on specific task knowledge, making them ideal for resource-constrained environments. The paper compares MOOSComp to existing methods, such as LLM-LINGUA2, which also uses a BERT-based compressor for binary token classification. While LLM-LINGUA2 is effective, MOOSComp improves upon it by addressing oversmoothing and adding outlier handling, leading to better compression ratios and performance. In terms of results, the researchers evaluated MOOSComp on several benchmarks for long context understanding and reasoning. At various compression ratios, it outperformed baselines in tasks like question answering and summarization, showing that the compressed prompts retained more essential information. For instance, at a 4x compression ratio, which means reducing the input to a quarter of its original length, MOOSComp achieved superior accuracy compared to other methods. Moreover, they tested it on a resource-constrained mobile device, where it delivered a 3.3x speedup in inference time. This is crucial for practical applications, like running LLMs on phones for real-time interactions, where every second counts and battery life is a concern. The overview figure in the paper illustrates this process clearly. In the training phase, you see the BERT encoder feeding into a classifier, with inputs including the original prompt and ground truth labels. The losses, cross-entropy and interclass cosine similarity, are applied to refine the model. In the compression phase, the figure shows how the classification scores are combined with outlier scores to make final decisions on which tokens to preserve or discard. By mitigating oversmoothing, MOOSComp ensures that the token representations are more discriminative, which directly translates to better compression quality. And by incorporating outlier scores, it handles the long tail of rare events in language, making the system more generalizable. This approach is particularly timely given the rapid growth of LLMs and their deployment in diverse settings. As contexts get longer, methods like MOOSComp will play a key role in making these models accessible and efficient for everyday use, from virtual assistants to advanced analytics tools. In summary of the technical details, the interclass cosine similarity loss is mathematically defined to minimize the average cosine similarity between positive and negative class embeddings. For a batch of tokens, it's calculated as the mean of cosine similarities between preserved and discarded token vectors, and then added as a penalty to the total loss function. This encourages the model to spread out the representations in the embedding space. During outlier score calculation, the researchers likely used pre-computed statistics from a large corpus, such as word frequencies, to assign scores on the fly. This integration is done by simply adding or multiplying the outlier score with the classification probability, depending on the implementation details. The paper also touches on related work, noting that while task-aware methods can be more precise, they often require expensive training or inference steps, whereas task-agnostic methods like MOOSComp offer a better trade-off for scalability. Finally, the authors highlight the potential for further improvements, such as adapting this to other types of models beyond BERT or exploring dynamic compression ratios based on input complexity. This positions MOOSComp as a foundational step in efficient long-context processing for LLMs.